Hi everyone. This lecture corresponds to section 17.1 of the openstax astronomy text. The material here should allow you to explain the difference between luminosity and apparent brightness and to understand how astronomers specify brightness with magnitudes. If you go outside on any clear night, you'll immediately see that some stars are brighter than other stars. The difference in brightness does not by itself tell us anything about how much light these stars are generating, because the brightness of a star depends on its distance as well as on how much light it actually emits. For example, the stars Procyon and Betelgeuse appear about equally bright in our sky, but Betelgeuse emits about 15,000 times as much light as Procyon. Procyon appears as bright because it's over 50 times closer. Because two similar-looking stars can be generating very different amounts of light, we need to distinguish clearly between a star's brightness in our sky and the actual amount of light that it emits into space. A star's apparent brightness is how it appears to our eyes. We define apparent brightness as the amount of power reaching us per unit area or per square meter. Luminosity is the total amount of power that a star emits into space. When we talk about how bright stars are in an absolute sense, regardless of their distance, we're talking about luminosity. For example, a 100-watt light bulb always puts out the same amount of light. Its luminosity doesn't vary, but its apparent brightness will depend on how far away you are from the bulb. The apparent brightness of a star or any light source obeys an inverse square law with distance, much like the inverse square law for the force of gravity. In equation form, the inverse square law of light says that the apparent brightness equals luminosity over 4 pi times the distance squared. Now consider this figure. We have a central star and 3 imaginary spheres spaced 1, 2, and 3 AU from the star. The same total amount of light must pass through each sphere surrounding the star. Pretend you're standing on the first sphere. You draw a square meter on its surface and you count the number of photons that pass through your square each second. Let's say you measure 4 photons. Now move to the sphere that is twice as far away and draw a square the same size. If you count the number of photons that pass through this square, you'll only count 1. Each square on the sphere twice as far away receives only a quarter of the light as the square on the first sphere. The light spreads out according to the inverse square law for light. Remember, the apparent brightness of a star is equal to the star's luminosity divided by its distance squared. In most cases, we can easily measure apparent brightness from Earth. It's just how much light we're detecting. The distance is often more difficult to determine, but we need it if we want to determine the luminosity using this equation. We'll discuss distance measurements in another lecture. To describe apparent brightness and luminosity, we use what is called the magnitude system. It was first developed by the Greek astronomer Hipparchus over 2,000 years ago. The magnitude system originally classified stars based on how bright they looked to human eyes. The brightest stars were called first magnitude, the next brightest stars second magnitude, and so on. The faintest visible stars were magnitude 6. These descriptions are called apparent magnitudes because they compare how bright different stars appear in the sky. We denote apparent magnitudes with a lowercase m. The magnitude scale is such that a larger number for apparent magnitude means a dimmer apparent brightness. For example, a star of apparent magnitude 4 appears dimmer in the sky than a star of apparent magnitude 1. Here are actual magnitudes of some familiar objects. Note that objects brighter than magnitude 0 go negative. For example, the full moon has an apparent magnitude of -13. The original magnitude scale was based on the human eye. Astronomers use a more precisely defined system today. The modern magnitude system also defines absolute magnitudes as a way of describing stellar luminosities. A star's absolute magnitude is the apparent magnitude it would have if it were at a distance of 10 parsecs from Earth. We denote absolute magnitudes with an uppercase M, and absolute magnitude allows us to compare stars by putting them all at the same distance. For example, the sun's apparent magnitude, or how bright it appears to us, is -27, very bright. If we were to move the sun to 10 parsecs away, it would appear dimmer, and we would measure an apparent magnitude of 4.8. Therefore, the absolute magnitude of the sun is 4.8. 4.8 is the magnitude the sun would appear at 10 parsecs. Knowing the apparent and absolute magnitude of a star can tell you something about its distance. For example, consider the star Deneb in the constellation of Cygnus. Deneb has an apparent magnitude of 1.25 and an absolute magnitude of -8. This means that Deneb appears to us on Earth to have a magnitude of 1.25, and at 10 parsecs, it would appear to have a magnitude of -8. And -8 is much brighter than 1.25, so Deneb appears brighter from 10 parsecs compared to viewing it from Earth. The only way for Deneb to appear so much fainter for us is if the star is located a lot farther away than 10 parsecs. Deneb is, in fact, over 800 parsecs away from Earth. As another example, consider Barnard's star in the constellation of Ophiuchus. Barnard's star has an apparent magnitude of 9.5 and an absolute magnitude of 13.2. In this case, 13.2 is fainter than 9.5. That is, Barnard's star would appear fainter at 10 parsecs than it does from Earth. For this to be the case, Barnard's star must be closer to us than 10 parsecs. It is, in fact, only 1.8 parsecs away from Earth. That's all for now. In the next lecture, we'll learn about stellar colors and temperatures. Take care, and I'll talk to you again soon.